So I have my spin indexer. I've mounted on the spin indexer this 3-jaw chuck, and in the 3-jaw chuck I've mounted an accurate bar, pin, or whatnot. Accurate? Not so important. What is important is that the bar that you're using be round in section. And what does that mean? That means that if I cut the bar at any place along its length, it always describes a circle. So how do I check if my bar or part here is really round at any place? Well, we have to measure at 5 or 6 different spots around the bar, along a line, okay, an imaginary line, then move over, measure again, then move over, measure again. All you're looking for here is that your 5 or 6 measurements in one position be the same. If they are, the part is round. Now you want to measure along its length just to make sure that it's always round, that there isn't a flat or maybe a little oval at one point on there that could give you a hard time or a bad reading. But your bar doesn't even have to be straight. It could be very slightly warped, that wouldn't be a problem. It could be mounted in the chuck a little crooked, and in this case it is, because I've shimmed one of the jaws so that the bar would be out of around in 2 axes, this way and this way. So just because I want to show the worst case scenario here. It doesn't have to be the same diameter everywhere, also, as long as it's round everywhere. And for that, well, you measure more than one spot. Now, if we look here, we can see that we're getting quite a bit of movement. As I mentioned, I want to show the worst case scenario, but what if I didn't have the worst case scenario? Well, the best case scenario here would be if the test bar is mounted parallel and concentric to the axis of rotation of the spin indexer. If that is the case, well, all I have to do to align this in rotation around its pivot point, well, would be to indicate the side of my test bar here and adjust to get it running parallel to the movement of the lower table. That axis, in other words. And that is really simple. However, you may be asking, well, if the head isn't aligned, how am I going to check that this is true and concentric? Again, it's a bit like checking the lower table. Putting an indicator on it won't help, but in this case it will. And it won't. Oddly enough, we don't seem to grasp that subtlety often. Things don't have to be straight to be true. Or parallel. Something that isn't parallel can be true, it can be concentric. So let's take a look here and see if I put a dial indicator at this end of the part here and I turned and I got no movement, well, that would mean that I'm concentric at that point. But I may not be concentric at the other. I may be concentric here but not there. So what do? I move over to a spot as far away as possible from the first, and I recheck. I come in contact and I check for motion. Even if I'm not at the same number, that's not important. All that matters is, do I have any movement at the start of the part, and do I have any movement at the end of the part? As we saw in this case, we have a lot of movement. But if I have no movement, I'm true and I'm parallel with the axis of the accessory here, my spin indexer, and then I just indicate the side, and as they say in Britain, Bob's your uncle. I never understood that expression. So if you could give me a comment, someone from England explain, or elsewhere, where does that expression come from? So that being said, worst case scenario is totally out of whack. And that doesn't matter either, because what I'm going to do is I'm going to align it on its center. Center is center. Whether something is moving out of alignment or not, it's moving or turning around a center. So all I have to do here really is go again from one point close to the chuck and check. In this case, seeing as I've skewed everything, well, it's going to be off and I'm going to get a lot of movement at the start. There's going to be a high point, there's going to be a low point, and the middle between the two is what I want as 0. So all I have to do is turn to find the high point, set myself to 0 on my dial indicator, turn to the low point, read how many thousandths of an inch I've moved, and then come back to the middle between those two, the 0 and the total movement. So let's say I had 10 thousandths of an inch total amplitude between the lowest and the highest. Well, I would then move to 5 thousandths of an inch. That would be the middle between the two. And then I would come and put my dial indicator to 0 there. That means that that dial indicator is indicating 0 on the center of the part. That's where the center should be. So I want to find my high spot. There it is. I'm going to set my scale to 0. Now let's find the low spot. We can see that that is 6.5. So 6.5. 0 to 6.5. I'm going to want to be at 3.25. So let's come back to 0, 1, 2, 3, and a tiny bit. There you go. And I'm going to bring my 0 to there. Now, am I at the midpoint? Let's take a look. Low point, high point. So about 3 and a bit over and about 3 and a bit under. I'm on this 0, the midpoint. So that is really 0 that indicates the center of rotation here. Now, without moving my dial indicator, and this is important, I'm going to head over to the other end of the part and start over. Now, this may have even more movement than the first because I shimmed one of the jaws, so this is going to be way out. And that's fine, because it doesn't matter how much movement there is, there's going to be a center point there between the high and the low. So without, and it's important, without changing the 0 on my dial indicator, I am going to find the high spot and I'm going to record where I am on my dial. I don't set a 0 here, you got to leave the original 0. So set that or record that dimension. Then I find the low spot and record that dimension. Calculate the difference between the two, and then, well, I move to the middle of that. If the middle of that second verification or measurement comes to the same 0 as the middle of the first, regardless of how much movement or difference in movement there are between the two, if they both come on center to the same 0, well, your headstock, or in this case spin indexer, will be aligned with the longitudinal axis of the machine. So if I look here, I have almost 3 thou over and I have almost 3 thou under. So my 0 point on this is really the 0 that we have here. Now let's move over to the other end and take a look at what we have there. Now I am not changing my 0 on the dial indicator. I'm not moving that scale because I want to check that the 0 is the same in both places. Now let's turn this and see what we have. So 5, 7 and a bit. Yeah. Yeah, there. Yeah, just barely over 7. And I'll say that is 7. So that is close enough. I mean, within 1/1000th of an inch here, which is no problem. Now that means that from 7 to 7, I have the same 0. 0 is the midpoint on my scale, and seeing that it is, and I'd set it to 0 at the first end, I know that this spin indexer is aligned with the axis of the table. So looking back at this whole alignment thing, there's really two things that need to be aligned for something to be ground parallel. And the first was the top table, or the upper table. The bottom one isn't adjustable. The top table is. And we want it to be parallel to the axis of movement of the lower table. And for that, well, all we had to do was apply an indicator to the side and move the lower table, seeing as I'm touching the upper table. If they are skewed one in relationship to the other, I'll see some movement there, and I can align or fine-tune that upper table. The other thing that is complex or difficult to align, a lot more difficult than the upper table, well, that is the headstock. Now, we can rotate it for some plunge grinding, as we've seen, but once we've offset it for some plunge grinding, let's say some angular plunge grinding, I'm going to want to bring it back to its proper position, especially if I'm going to want to hold parts between centers eventually. It's going to have to be very well aligned with the center in the tailstock. Well, first off is to get it really straight, let's say without using the tailstock. Well, I would use this bar that I've measured and made sure that it's accurate. And holding it in, I did it in a 3-jaw just to make it a little more complex. But let's say holding it in a 4-jaw chuck, centering one position close to the chuck jaws, and then setting my indicator to 0 on that concentric position. So I got no movement, and I set it to 0. Then I come out to the other end and check it and see, am I getting 0 movement here also? If I am, well, it's mounted concentric in the chuck, the 4-jaw chuck, and my whole headstock is nice and aligned. I've got the same 0 at one end to the other with no movement in either. Now, however, let's say that I'd align this end to 0, the one closest to the jaws, and then I come out to the other end without changing the 0 on my dial indicator, and I see that, oh, I have some movement here. It's moving 6/1000ths of an inch every time I do one full revolution. Is that a problem? Well, not necessarily. If you see that it's 6/1000ths of an inch from one side to the other, so 3/1000ths of an inch below 0 and 3/1000ths of an inch above 0, well, that means that even if you're skewed a little bit, the center is the same as the first one because its midpoint is the same 0 that you had at the start. So you don't have to make yourself sick trying to find the perfect bar and get it perfectly concentric in your headstock to find if your headstock is aligned. The other thing that we can do is use a dial indicator and indicate the center in the tailstock to ensure that my headstock is properly aligned. To finish things up, let's take a look at speeds, feeds, and wheel wear. It's very different what happens on the lathe, and we've been comparing our cylindrical grinder to the lathe quite a bit. Well, here are some major differences: speeds, feeds, and wear. First off, well, the obvious difference is that on the lathe, the tool is fixed. I mean, it can be moved in X and Y, but it is not a rotary tool. It is a fixed tool. That's not the case on the cylindrical grinder. The grinding wheel moves. It turns as well as moves. And that means that it has its own cutting speed. But the problem also is that the part turns, as is the case with the lathe. So the speed that the part turns in relationship to the speed that the wheel turns, well, affects the grinding action or the cutting action. The other main difference here is that on the lathe, the feed of the tool along the part is intertwined or connected to the speed of rotation. There's only one motor on the most lathes that drive both components. And well, that means that on the lathe, if I set my feed to, let's say, 6/1000ths of an inch per rev, or a normal cut, well, that means that every time the head turns once, my tool advances 6/1000ths of an inch. If I speed up the rotation of the part, the feed adjusts in consequence and always maintains that 6/1000ths of an inch if that's what I set. That's not the case on a cylindrical grinder. On a cylindrical grinder, the table's movement is controlled by one hydraulic system, and the head and the motor's rotation are controlled by separate systems. So, and they are all intertwined. And that, well, makes for a big difference, because not only do you have 3 different adjustments that affect the same thing, but the head can actually turn in one direction or the other, clockwise or counterclockwise. And that means that it can cut with the direction of rotation of the part, or it can cut against the rotation of the part. And that makes a huge difference. So let's try and make a little sense of all this. We'll head over to the whiteboard and see what we can come up with. When you're grinding, removing material with a grinding wheel, it's all about volume. Volume is how much material you're removing in a unit of time. And as I've just mentioned, there's no real relationship in the machine between the speed of your feed and the speeds of your RPM for the part and the RPM for the grinding wheel. That makes for many different situations, especially when we think that parts come in different diameters. Now, when we are surface grinding, we always have a circular wheel, and it's always up against a flat part. So if you're used to surface grinding with a 10-inch wheel, well, you get used to quickly knowing what depth of cut and what feed you can get away with when you're working, because you're always working on a flat surface. Cylindrical grinding is a little more touchy, because it's cylindrical surface of a wheel against cylindrical surface of a part. And the diameter of the part, each different diameter, is going to react a little differently. Actually, the larger the part gets, the more it acts like a surface grinder. And the smaller it gets, well, the less that it acts as a surface grinder. So let's take a look at contact, because that is what the name of the game is as far as the problem that I'm talking about. If I have a large wheel, and you can see this is the wheel because of the dots that I've drawn, you can see that this is very high tech, and this is my part that is of a small diameter. This is the situation that has the least amount of contact, small against large. So that small point of contact means that I can take a deeper amount, a deeper cut. But there's a downside. Deeper cuts here is going to apply more pressure on the part, and this part is quite small. So even if I could theoretically remove more material faster on this small diameter part, I can't really, because the part is small and delicate. Here we have the same wheel and a part that is quite a bit larger. And this is really what you're looking for, if possible, the relationship of about 2 to 1. So we have our part here. Great. It's reasonably large, so I'm going to have to take more shallow cuts, but my part is a lot more rigid. So maybe I can push this a little harder. And we see that that relation really changes. And there's all kinds of different diameters, so that means you're constantly having to adjust what material, what wheel, what diameter of part, it all changes. If I look down here, what is this? This is internal cylindrical grinding. And I have my very small grinding wheel here, and I have the hole in the part that I'm grinding. This is really the worst situation for as far as contact goes. This is plus contact. Why? Because I have a curved surface that's coming up to a curved surface that's curved in the same way. And that is, when this comes into that, the maximum of contact. I can take only very, very shallow cuts, and I can do that as long as my wheel is noticeably smaller than the hole that I'm grinding. If this wheel was half the diameter of the hole, I would really not be able to take very much off. And the smaller that grinding wheel gets in relationship to the hole that I'm grinding, well, the deeper the cut that I can take. Then again, I mean, there's a downside to that. If I use a very small grinding wheel so that I can take deeper cuts, well, I'm going to be removing a lot of material, but I'm going to be wearing down my grinding wheel faster. And that is a problem because the grinding wheel is tiny. There's not a lot of abrasive there to wear off. And if you don't want to have to dress your wheel at each pass, well, you might want to slow down a little bit or take it a little lighter as far as depth of cut goes. But there's a speed thing as well. A small part can turn quite fast. A medium part will turn slower. I mean, that's the same as we've seen on the lathe. And an internal grinding situation, the part is going to turn very slow. And the grinding wheel is going to go very fast, way faster than these grinding wheels here, because it's tiny. If I want to keep my surface feet per minute up, it's going to really have to motor as far as RPM goes. So that's my basic principle, but there's something else that affects the cutting action here. We have the RPM of the wheel, the RPM of the part, fine. I understand the contact. What's this here? Well, it's surface feet per minute. And when we're cutting, we're used to hearing cutting speeds in surface feet per minute. Well, grinding is no different. The surface feet per minute are going to be quite high. But the direction that things are turning in really makes a big difference. Generally speaking, it's the part that can be reversed or turned in one direction or the other. Generally, the grinding wheel only turns in one direction, mainly for safety reasons, because the guards are set up for that direction of rotation. And that means that the little sketch that I've made here isn't right at all, because I have the wheel going up in this direction and the wheel going down in this example down here. This is not right. It's the part that I should have reversed, but bear with me, I'm lazy and I really don't feel like redoing the whole thing. So what we have here is two wheels that are turning in a clockwise fashion, and that means that at the junction point they are opposed one to the other, and that increases the speed that we're cutting at. So I say more surface feet per minute. It's acting as if I was cutting at a higher rate of surface feet per minute. If I want to slow down, I can slow the rotation down on the part. And I can put the part in opposing rotations, which means that at the junction point they'll be moving in the same direction. And that reduces what is our surface feet per minute, or the speed of cutting. And that's important because the part, again, is variable. It could be quite large, it could be quite small. And I don't necessarily have all the adjustment possible on the grinding wheel speed to compensate for all those different diameters. And by changing the direction of rotation and the speed of rotation of the part, well, I can really get a wide range of different speeds of contact between the two. Very important, not just to cut any RPM with any RPM of a grinding wheel. It really has to be fine-tuned to the diameter of the part that you want to cut. The larger the part that you're going to cut, the more you're going to tend towards opposing rotations. And the smaller the part, the more you're going to tend towards the same direction of rotation. something to keep in mind. The last thing that I want to mention in this series of videos is, well, the feed. Now, we've seen speeds of rotation. What about the feed? Well, feed here is independent. We've mentioned that. So I can make the table feed at whatever speed I want. And really, the cylindrical grinders that I've used in development shops don't really have accurate feed settings. You sort of have to go by eye. But there's some basic rules, and that is that the larger the part, the slower that you're going to want to feed, and the slower that you're going to want to turn. Why do you want to feed slower? Well, you want to maintain a light helix angle. Now, if you have a large diameter part and you feed the work quickly, you're going to get a very pronounced helix angle on the part. And that means that you're going to be wearing a wide portion of your grinding wheel in one single turn. You're going to be contacting almost full face of the part. It's not a good situation unless you're plunge grinding, and if you are, well, you're not using the longitudinal feed in that case. In this example here, you can see that the feed is way too high in relationship to the speed of rotation for the diameter of this part, and we get a very pronounced helix angle. This is not a good situation. So you really want to adjust things for their diameter. The smaller the diameter, the faster you can feed, but then again, as mentioned, the smaller the diameter, the lighter the part, so maybe you won't want to push it too much. The larger the part, well, the slower you're going to want to feed, and the slower you're going to want to turn. Well, I hope that helps. Now, I realize that in most home shops there won't be a cylindrical grinder, so this isn't something that most of you are going to use, but it is nice to know. So until we meet again, have fun, but be safe. If you're not safe, I'm going to come and get you. And happy machining.
So all I ever wanted was a little monkey from you.